Welcome, folks. First video on advanced techniques of integration. In this video, we're going to be talking about integration by parts. Integration by parts, as it turns out, is motivated, for instance, by the following integral, the integral of x cosine x dx. So at the moment, we don't have any strategies to evaluate this integral. A couple observations. No substitution that we can think of is helpful. I'll let you press pause for a minute and try out a few. And then because there's a product in the integrand, we might expect a product-like rule in a strategy for finding an antiderivative here. And that turns out to be exactly what integration by parts is. It's just a product rule written a different way. So we'll start off giving you some background. We'll do a couple definite integrals, and then we'll see some other applications of integration by parts. So here's a background. We know that when we want to find the derivative of the product f times g, we can write it as the first times the derivative of the second, plus the second times the derivative of the first. And if u is f of x and v is g of x, we can also write this relationship in differential form. So here's that relationship in differential form. The derivative of a product uv is the first times the derivative of the second, plus the second times the derivative of the first. Now, rewriting that and then integrating both sides gives us what's known as the integration by parts formula. So solving for u dv, we can find antiderivatives of both sides, and the antiderivative of that derivative, uv, ought to just be uv itself. So this, as it turns out, is the integration by parts formula. So again, here is that formula. The integral of u dv is u times v minus the integral of v du. And our general strategy for evaluating integrals using integration by parts is to choose u and dv. From that, we can compute v and du. Writing down the formula, the new integration, the new integral we find in our formula here should make your life no worse. And see what we mean by that in a minute. Okay, here is an example, the motivating example. So I'll go ahead and rewrite the integration by parts formula here and choose u and dv accordingly. So here's u and dv, computing du and v. We can see that the integral of x cosine x ought to be x sine x minus the integral of sine x. Now this new integral we have on the right side has made our life better. The integral of x times cosine x is worse than the integral of sine x, and in fact we know how to find an antiderivative in this case. So we can just write down the integral. So here is that indefinite integral, in this case, x sine x plus cosine x plus c. And of course, it's quick to check. One can just take the derivative of this expression in the box and see that you come up with x cosine x, which shows that that's the antiderivative of x cosine x. Okay, super. Here's another example. Let's go ahead and have a look at the integral x squared e to the 2x dx. So same strategy here, choose u and dv, compute v and du, write the integration by parts formula, and hope that your new integral is no worse. So here's integration by parts applied to this integrand. U is x squared, dv is e to the 2x. We can compute du is 2x dx, and of course v is 1/2 e to the 2x. So the integral of u dv is u times v minus the integral of v du, and I've just canceled out those factors of 2 and 1/2. Now we can see that we're left with a new integral, x e to the 2x, that looks a little bit better than our original integral of x squared e to the 2x. However, it's still a product, so it suggests that we try integration by parts again, just on this term. So here's integration by parts again, applied to just the new integral after the first application. So that new integral becomes this once applying integration by parts. And we can see again that the integral we're left with, we're better off. So go ahead and evaluate that integral e to the 2x and write down the antiderivative in this case. So I've gone ahead and written that general antiderivative below. Sometimes it's convenient to express that general antiderivative in a factored fashion like we see above, factoring out the exponential part. So either way is fine. Okay, one more example. Here's another example, the integral of e to the x cosine x dx. So we'll go ahead and use integration by parts, just like we did before. So here's one application of integration by parts to this integral with u equal to e to the x and dv equal cosine x dx. We see that du is e to the x dx and v is sine x dx, and the integral of u dv is u times v minus the integral of v du. We can see that we're left with an integral that, while may not be better than our integral before, it's at least no worse. So this is what I mean when I say the new integral should be no worse. Using our intuition from last time, we'll go ahead and try integration by parts on this new integral. Okay, so here's integration by parts applied to our new integral there underlined in green. When u is e to the x and dv is sine x dx, we can compute that du is e to the x dx and v is negative cosine x. From that, we can write down that the integral of e to the x cosine x dx is e to the x sine x minus the quantity minus e to the x cosine x minus the integral of minus e to the x cosine x dx. Okay, so there are a lot of minus signs here, and it almost looks like we're sort of going in a circle here, and we almost are, but we'll see why that ends up being useful in just a second. So let's clean up the minus signs and we'll see where we stand. So after cleaning up the minus signs, we see that we've come up with an equation where what we've done is actually reproduce the original integral. So here's what I mean by that. That integral is this one right here. So we can go ahead and manipulate this equation algebraically by moving that integral to the left-hand side and coming up with two of them instead. So again, here's an expression where we've moved our integral on the right-hand side over to the left-hand side so that there are now two of them on the left-hand side of our equation. So two integrals of e to the x cosine x dx is e to the x sine x plus e to the x cosine x. Just divide through both sides by 2, and I'll do a little bit of factoring, and we'll see that we have the desired integral. So here I've factored out the exponential term, divided both sides by 2, and of course, since we want the general antiderivative, go ahead and tack on a factor of plus c. Okay, so this is the general antiderivative for e to the x cosine x. If you're not sure, you could take the derivative and find out. And again, this strategy is called reproducing the original integral. It turns out to be sort of a common strategy in integration by parts. Okay, a couple more examples. Here is an integral for which there's really no choice of u and dv, but we'll go ahead and make u the natural log function because we know how to take a derivative of that function. So here's integration by parts applied when u is the natural log of x, dv is dx. We can see that du is 1 over x dx and v is x. And the integral of u dv is u times v minus the integral of v du. Now, of course, that second integrand just simplifies to the integral of 1 dx, and we can quickly evaluate that to find the general antiderivative in this case. So here we see that general antiderivative, x ln x minus x plus a constant. And again, here we can go ahead and just take the derivative of this expression to check that we have the right antiderivative. Okay, let's go ahead and have a look at integration by parts on definite integrals. There are two different strategies here. One strategy is to carry the limits with you throughout the integration process. Another strategy is just to use integration by parts to find an indefinite integral and then go ahead and use that in the fundamental theorem of calculus. So they're both correct, and sometimes one is easier than the other, but you won't go wrong with either. So in general, the integral of u dv from x equals a to x equals b is u times v evaluated from a to b minus the integral of v du, again, from a to b. And I go ahead and write these limits here as x equals limits just to remind us that those are x values inside of the definite integral. And just to remind you here of an alternate strategy is just to evaluate the indefinite integral and then use the fundamental theorem of calculus at the end of the day. So either of those are correct. Okay, a couple examples with definite integrals and integration by parts. Here's the first one. Let's go ahead and have a look at the integral of arctan x dx. Now, once again, this isn't something that we know an antiderivative of right away. So similar to the natural log of x, we'll go ahead and let u be arctan and let dv be dx. So here's integration by parts applied to the original integral from 0 to 1 of arctan x dx. We find that it is equal to x arctan x evaluated from 0 to 1 minus a new integral from 0 to 1 of x over 1 plus x squared. Now this integral, as it turns out, we can evaluate using a substitution method from chapters 5 and chapter 6, as it turns out. So the substitution here is the denominator 1 plus x squared. And I'll go ahead and do the substitution formally. Since I've already used u as a variable, I'll do a w substitution here. So here is that term x arctan x evaluated at 0 and 1. And here's our substitution. Our new integral is the integral from 1 to 2 of 1/2 1 over w dw. We can see that the first part in the square brackets evaluates quickly as pi over 4. Of course, arctan of 0 is 0. And the second part integrates up like a natural log function, which we can evaluate at the endpoints. So here's that antiderivative. 1 over w dw integrates as natural log of w. Arctan of 1 is pi over 4. We end up with pi over 4 minus 1/2 times the quantity natural log of 2 minus natural log of 1. Everyone knows that natural log of 1 is 0, and the definite integral in this case is pi over 4 minus 1/2 natural log of 2. Here's another example. Let's go ahead and have a look at the integral from 1 to 3 of x natural log x dx. Now, we've dealt with natural log in one of these integration by parts examples before, and before we saw that it was convenient to let u be the natural log function. So we'll try that again here. So here's our integration by parts formula applied to the integral from 1 to 3 of x ln x dx. We find that it's 1/2 x squared times the natural log of x evaluated from 1 to 3 minus a new integral from 1 to 3 of 1/2 x dx. U times v minus the integral of v du. Now this new integral evaluates quickly as 1/4 x squared, and we can evaluate that between 1 and 3 also. So here we've applied integration by parts, evaluated the new integral, and this time I went ahead and evaluated the whole thing between x equals 3 and x equals 1 to find that the value of the definite integral is 9/2 times the natural log of 3 minus 2. Okay, let's go ahead and look at a couple other applications of integration by parts. Here's the first one. Let's have a look at the integral of cosine of the square root of x dx. Now, it's not obvious that integration by parts applies here. However, when we make a substitution of the part of the integral that's annoying, namely the square root of x, we can see that integration by parts falls right out. So let's try y equals the square root of x. So here's that substitution. Y equals the square root of x, or in other words, x equals y squared, so that dx is 2y dy. We can see that the integral of cosine squared x dx is the integral of cosine y times 2y dy, which we can factor and write as 2 times the integral of y cosine y dy. Now this, as it turns out, is exactly the integration by parts integral we started the class with. So I won't go through the details, but you can refer to that previous example, and I'll just write down the definite integral or the indefinite integral here in y world. So here's that indefinite integral in y world. Y cosine y dy integrates to y sine y plus cosine y. That was our previous example. And then we can go back to x world to write this as 2 times the quantity squared x sine squared of x plus cosine squared of x, all plus a constant c. Okay, let's look at a couple other examples. Here's the first one. Let's suppose that the region R is bound between the x-axis and the curve y equals natural log x on the interval from 1 to 3. Let's start by finding the area of that region R. So we'll start by graphing the region R and then writing down an integral that represents that area. So here's a natural log function against x, as x ranges from, I guess here we've gone x greater than 0, and the region between 1 and 3 is the region shown. So we can see that the area of this region R is just an integral from 1 to 3 of the natural log x dx. So we've seen this integral before too. We found the general antiderivative of the natural log x to be x natural log x minus x, and we'll just evaluate that between 1 and 3 to find the area of the region in this case. So here's our definite integral in this case, 3 natural log of 3 minus 2, and I've written this as units squared because our number in this case represents an area. Okay, let's go ahead and think about the volume of the solid if the region R is rotated around the y-axis. So we're familiar with this idea of taking a slice with width dx, rotating that slice around the y-axis. In this case, we obtain a cylindrical shell. We're familiar with this from our previous applications of the definite integral. We know that the volume of that shell is 2 pi r h dx. And we know that the radius in this case is x, and that the height is a natural log of x, and we can express our volume, therefore, as an integral. Now, I won't go through the details in all of their glory here either, but we've actually evaluated this definite integral as well, x ln x dx, where x goes from 1 to 3. So I'll just write that as 2 pi times the quantity 9/2 natural log of 3 minus 2, and again, expressing things in terms of cubic units because we have a volume. Okay, let's go ahead and think about, similarly, the region obtained if we rotate the volume of the solid obtained if we rotate the region R about the x-axis. So here's our disk with radius R. We know in this case that radius is a natural log of x. Using our definite integral to add up all of these little bits of volume, pi r squared dx, we can see that the volume of the entire solid should be the integral from 1 to 3 of pi times natural log of x quantity squared dx. So we'll just try integration by parts here with u equal to the natural log squared and dv equals dx. We can see that du has to be 2 times the log of x times 1 over x dx, and that v has to be x. Using integration by parts formula, we can write our integral as u times v minus integral of v du. So we're left with pi times the quantity x natural log of x squared, evaluated from 1 to 3, minus a new integral from 1 to 3 of 2 times the natural log x dx from, again, from 1 to 3. Now this second integral is one that we just did, and the first one is one that we can evaluate quickly. So I'll just go ahead and write those two down. So again, here the first part comes from evaluating this quantity from 1 to 3. Of course, the natural log of 1 is 0, which simplifies quickly. And the second part comes from integrating the natural log x from 1 to 3, which we did previously and got 3 natural log of 3 minus 2. Okay, folks, that's it for our integration by parts video. A lot of examples here. Hope you have a great day, and we'll see you next time. Bye-bye.